So we're going to continue our discussion today with various aspects of C++ templates. We'll begin by talking a bit more about C++ function templates, comparing them to macros and the C++ preprocessor. And then we're also going to talk about some more advanced features of C++, some older school stuff about instantiating templates. And then we're going to go ahead and talk in a later video about topics related to some template metaprogramming issues and other advanced features such as variadic templates. So if you want to find the code we'll be covering here, it's going to be in my GitHub repository in the C++ STL S-02 folder in the 2.8, 2.9, and 2.10 subfolders. So with that, let's go ahead and switch over to my IDE. So the first thing we're going to talk about are things related to the differences between template functions and preprocessor macros. At a high level, they do somewhat the same kind of thing in the sense that a macro can be parameterized and those parameters can be expanded at compile time, and you can have variadic arguments. You can have arguments whose types will be bound late in the programming cycle because they're just text expansions from what's passed to them. So, for example, you can have a min macro that takes parameters I and j, and you can give it longs, you can give it ints, you can give it characters or doubles or floats or shorts or whatever, and it doesn't really care. It just goes ahead and blindly expands them. And if you look carefully at that min macro with the capital MIN, you'll see that it has a whole bunch of parentheses that basically encompass the I less than j question mark expression. And if I is less than j, we return I, otherwise we return j. And there's so many parentheses here, it looks kind of like Lisp. So that particular way of doing things has been around for a really long time, going back to probably the early 70s with the C preprocessor, but it turns out to be very problematic for reasons we'll discuss in just a moment. To fix a lot of those problems, C++ provides template functions, and they give you pretty much the same capabilities that the macro does, in the sense that you can have a min function that's going to be parameterized by ints or shorts or longs or doubles or floats or chars or whatever. And you can see that the actual expression is very similar. We have a min function with lowercase min. It's parameterized by type t. We take two parameters I and j, which are const t-refs, and it returns a t. And the actual expression looks similar to the macro. It's I less than j, question mark, I, colon j. Except we don't have all those crazy parentheses because normal function semantics apply and it's not doing text expansion. So why do we like the templates and the template functions more than macros? Well, it turns out that there's a bunch of problems with macros. First and foremost, the C++ compiler can't verify that the macro parameters are the right types because it doesn't do any type checking. It doesn't even see the code. It's been expanded by the time the compiler gets run on the code. And the other big problem with macros, of course, is the fact that it just does blind text expansion. So in this particular case, for our min macro, the parameters I and j will be evaluated twice. So as you can see here, if we have a equal 10 and b equal 20, the macro version will expand to a++ less than b++, question mark, a++ colon b++. So a and b will be incremented twice, which is going to lead to crazy results, as we'll see. In contrast, the template version of this, which is a++, comma b++, for min, the function, a and b will be evaluated and passed as parameters to min, and min will compute the min of 10 and 20, giving back 10, of course, and then a will be incremented and b will be incremented, but that won't affect the way that min works. So the way of looking at that is that the parameters are captured and passed to the function before they're actually incremented. Another tricky part, of course, is that macros, since they're expanded by the preprocessor, it's very difficult to set breakpoints in the macros because the compiler doesn't even know that they exist. Some compilers will help you with this, but most don't. Most don't have tight coupling between the preprocessor and the compiler. So you just are out of luck when you try to debug your code, unless you know what the macro expands to, and that's complicated too. So let's go ahead and take a look at this example and see what's wrong with it when we run it in practice. As I mentioned before, a is set equal to 10, b is set equal to 20. and then we're going to compute min with the template and then min with the macro. And for both versions, we're going to increment A by 1 and increment B by 1. And let's take a look, and we'll run the code, see what the results are, and then we'll talk about it. So as you can see here, what we have as the results are that the function version ends up returning 10, which is what we expect, but the macro version returns 12, and then A is set equal to 13 and B is set equal to 22, which is just completely wacky and crazy. And if you take a look, the reason for this is pretty clear. The min function is going to get A and B before they're incremented, whereas the min macro is going to expand all that stuff in line, getting these crazy results. So the bottom line, there's very few good reasons to use macros in C++ anymore. About the only good reason left is to do include guards, which we've talked about before, for header files and for the .cpp files for templates. Those are about the only good reasons to use macros. There's one other reason: if you do compilation, it has to be modified by command line parameters, but let's ignore those for the discussion here. Everything else has been subsumed by other features like consts and templates and other kinds of things. Okay, so that's the end of that first example. Now let's go ahead and take a look at another example, and we're going to find that one down here in, I think this is in the 2.9 folder. There we go. So I'm going to start out this discussion. So I want to start out this discussion by comparing and contrasting the way you compile and link traditional C code, classes and functions that are not templatized, with code that's templatized. So for traditional classes, like the data abstraction stuff we talked about earlier before the advent of generic programming, you would typically put your class definition in the .h file, all the methods and the private data members and so on, and then you would put the implementations of those member functions inside the .cpp file. And you'd include the .h file in the .cpp file, and you would separately compile the .cpp file into some object file, like a .o file or a .so file or a .dll, whatever your platform needs. And then from there, you would go ahead and have that linked together, and you run your program, you run your executable. With templates, things change. The C++ compiler needs to see the template implementation in order to be able to instantiate it properly at compile time and link time. And so as a consequence, it needs the source code. So what happens there is, instead of having your .cpp file hash including your .h file and being separately compiled, instead you have your .h file hash including your .cpp file, and then that gets compiled in with other parts of your program. Now, this is a little bit strange at first, but you get used to it very quickly because you really don't have much other choice. And so as a consequence, it's important often to be able to put the inclusion guards around the contents of the .cpp file, just like you would do with the contents of the .h file in the other context. Now, one of the things to realize here is that you can end up including the header and CPP files a lot of places in your code. And in older compilers, this would cause all kinds of problems. In fact, we're going to talk about some problems with older compilers here in just a second. But with modern compilers and smarter linkers, they're able to avoid duplication of symbols by taking a look at all the object code that's produced when you go to link everything together into a final executable, and then removing duplicates. So smart linkers can go a long way towards avoiding unnecessary code bloat in code that uses templates. 15, 20 years ago, that was not the case. Templates were given a bad rap of being bloated, but that doesn't really happen anymore. Now, one problem that also used to happen back in the day is that sometimes the compiler and linker would get confused and would fail to instantiate the templates properly. Now, remember the way that templates work. When you have a template class with a bunch of member functions, you have template functions. Only the functions that you actually use get instantiated. So you could have a template class with 200 methods in it, and if you only use 2 of them for, say, double or int or whatever, then only that code for those 2 methods for those types will get instantiated. And the same thing applies also for function templates as well. So this lazy generation of object code is a good thing, but older compilers would get confused. So there was a feature that was added to C++ to avoid the confusion called explicit instantiation. And so I'm going to talk briefly about explicit instantiation. If you're fortunate and never have to work with legacy code, you'll never have to worry about explicit instantiation. But if you get stuck on a project with older compilers or maybe an embedded system that's using older compilers, it's sometimes useful to know about this. We'll also get a chance to write a little helper method that is parameterized by type T, and it prints out the name of the type information that we're passing into it. So we'll get a chance to see that too. Okay, so down here, we're going to define a template class called example class. You can see it's parameterized by type name T, and it's got a default constructor, it's got a method called result, and it's got a method called add. And they all work with the parameters T that are parameterized. And then what I'm going to show you next is how you can explicitly instantiate various standalone methods like our print data type function. And you can also instantiate member functions, and you can also instantiate entire classes. And this is, again, was something that was necessary back in the day when you had to get full control over instantiating templates. So here we've got some instantiations of print data type for int and double. Here we have an instantiation of the constructor for example class for int. Here we go ahead and say, I want the entire member functions for example class instantiated for type double. So all those methods will be instantiated. And then down here, we can go and explicitly instantiate the constructor, the result method, and the add method for string. So those are all examples of how to do explicit template instantiation. And the last thing I'm going to do here is just make myself two objects of example class, one that's parameterized by int, one that's parameterized by double. And then I'm going to go ahead and print out the data type of both of those things. And we'll see how the C++ compiler encodes the information about these objects. So you can see here when we print the type information out for example class parameterized by int, it turns into 13 example underscore class, which is an encoding of the name of the class prefixed with its length in characters. And then we also have some other encoding here that says it's parameterized for int and so on. And then you can see the same thing is done here, except this time it's parameterized for double. So it has a little d instead of a little I. And this type of encoding is actually used by the C++ compiler as part of its runtime type identification mechanisms to do things like determine whether two classes are related to each other by inheritance. Okay, so that was the first part of the video I wanted to talk about. I just wanted to talk briefly about explicit template instantiation, and I also wanted to talk to you about how C++ templates and template functions improve upon and remove the need for many of the tedious and error-prone aspects of programming with macros.